Welcome to the deep dive. Today, we're tackling a topic that's absolutely fundamental to our modern world, even if it often just hums away in the background. We're talking electrical machines.
That's right. We mean the devices that, make our lights turn on, our factories run, even our electric vehicles move. They're really the unsung heroes of energy conversion.
Taking power in one form and transforming it into something else we can actually use.
Exactly.
And for this deep dive, learner, you've pulled together a great set of sources. Looks like they cover, well, everything from the core principles, how they're built, to all sorts of applications.
Yeah, it spans from basic definitions right through to some really specialized machines.
So the mission, learner, is to really grasp the core ideas behind these things. They're everywhere. But without getting totally bogged down in, dense technical jargon.
We want to pull out those aha moments.
Yeah.
Find the surprising bits, make sense of the fundamentals. Think of it as your shortcut to getting what makes these machines tick.
Okay, let's start unpacking. So electrical machines, broadly speaking, we're looking at three main players.
Pretty much. First up, you've got generators.
Generators. Okay, so they take mechanical energy, maybe water turning a turbine or wind.
Right, that kind of thing. And they turn it into electrical energy. It's like energy alchemy.
How do they actually do that? It's something about magnetic fields.
It is. It boils down to this thing called dynamically induced EMF, electromotive force. Basically, move a wire through a magnetic field.
Like waving it through the field?
Yeah, precisely. That movement, cutting across the magnetic lines, it actually generates a voltage in the wire. It pushes the electrons, creates current.
Motion and magnetism working together. Cool. Okay, so second type.
Motors, which are in a lot of ways the opposite of generators.
Right, they take electrical energy in.
And turn it into mechanical energy. Motion. Think about your fridge compressor.
Yeah.
Or an electric train engine. That's a motor doing the work.
What's the principle there? More magnetic fields?
Definitely. You run current through a wire that's sitting in a magnetic field. That wire creates its own magnetic field.
Oh, okay.
And these two fields, they interact, they try to align. That creates a force. And in a motor, that force is cleverly channeled to make something spin, to create torque.
Okay, generators, motors, and the third one.
Transformers. Now, these are interesting. They don't change the type of energy like mechanical to electrical. They stick with electrical.
But they're vital for AC power systems, you said.
Absolutely critical. Their job is to change the AC voltage level. Step it up or step it down.
Why is that so important?
Efficiency, mainly.
Mhm.
For sending power over long distances, you want really high voltage to minimize losses in the wires. Transformers step it up at the power plant.
And then step it back down near our homes.
Exactly. Down to safer, usable levels. They're the backbone of the grid, really, operating on mutual induction between coils.
Okay, that's a great overview. Before we dive deeper into each one, maybe we should touch on some common concepts, things that apply across the board.
Good idea. Yeah. Like basic circuit concepts. Your sources definitely cover this.
Right.
An electric circuit. It's just a closed path, right, for current to flow.
A loop. And the current itself, the flow of charge, that happens because there's a voltage pushing it.
Yep. An electromotive force or voltage pushing against some kind of resistance. Voltage is the pressure. Resistance is the opposition.
More voltage, more current, more resistance.
It's less current. Simple relationship. Ohm's law, basically.
And resistance isn't just one value, is it? It depends on the material itself.
Right. Some materials resist more than others. Copper versus rubber, for instance.
And the shape, like a wire.
Yeah, the physical dimensions matter. A longer, thinner wire has more resistance than a short, thick one. It's like pushing water through pipes, narrow pipe, more resistance.
Okay, circuits. What about the magnetic side? You mentioned magnetic circuits as an analogy.
It helps a way to think about it, yeah.
Yeah.
Instead of voltage, you have magnetomotive force, MMF. Think of it as the magnetic push.
Generated by current in a coil.
Exactly. And that MMF establishes magnetic flux. Instead of electric field intensity, you have magnetic field intensity, H, which is like MMF per unit length of the magnetic path.
So flux doesn't really flow like current.
That's a key distinction, yeah. It's less like water flowing and more like alignment. The MMF causes tiny magnetic domains inside a material to line up. That collective alignment is the magnetic flux. It gets set up rather than flows.
Ah, okay. Alignment, not flow. Got it. And flux density.
Just tells you how concentrated that magnetic field, that flux, is in a specific area. Flux per unit area, usually called B.
Right. Now, You mentioned dynamically induced EMF for generators. That seems super important.
It really is. Conductor moving, cutting across a magnetic field. That's the heart of it for generators.
And the amount of voltage you get depends on.
Three things, mainly. The strength of the magnetic field,
Yeah.
the length of the conductor actually in the field, L, and how fast it's moving, V.
So stronger field, longer wire, faster movement, more voltage.
Precisely. The formula is quite neat. EMF equals B times L times V. Increase any of those, you boost the voltage.
We also need to talk about inductance, right?
Yeah.
Self and mutual.
Yep. Self-inductance is like inertia for current. A coil resists changes in the current flowing through itself. It creates a back voltage.
And mutual inductance, that's between coils.
Exactly. Changing current in one coil creates a changing magnetic field, which then induces a voltage in a nearby coil. That's the magic behind transformers.
And there's something called the coefficient of coupling.
K.
Yeah.
K basically tells you how well those two coils are linked magnetically, how much of the flux from one actually goes through the other. K close to 1 means a really tight link, very efficient energy transfer, like in a good transformer.
Your sources probably also get into how inductance adds up when coils are in series or parallel, considering that coupling.
They likely do, yeah. It gets a bit more complex than simple resistors because of that mutual interaction.
Okay, solid foundation. Let's switch gears to motors, turning electricity into motion, starting with DC machines.
Right, DC motors. The big challenge there is getting continuous rotation. Simple loop would just oscillate back and forth.
So how do they fix that?
The commutator. It's this really clever mechanical switch on the rotating part, the armature.
What does it do?
As the armature spins, the commutator reverses the direction of the current flowing into the armature coils at just the right moment.
When does it switch?
Just as the coil passes through the point where the magnetic force would naturally reverse. By flipping the current direction, it ensures the force, the torque, always pushes in the same rotational direction. Smooth, continuous spin. Ingenious, really.
Okay. Now, the sources distinguish between shunt and series DC motors. What's the difference in practice?
It's all about how the field winding the part, creating the main magnetic field, is connected relative to the armature winding. In a shunt motor, they're in parallel. Shunt means parallel.
And what does that parallel connection do?
It means the field winding gets the full supply voltage, more or less. So the magnetic field strength stays pretty constant, regardless of the load on the motor.
Which affects the speed.
Right. It leads to a motor that runs at a fairly constant speed, even if the mechanical load changes quite a bit. They also have, decent starting torque, good all-rounders.
Okay, so that's shunt. What about series motors? Field winding in series, I guess.
Exactly. Field winding is connected in series with the armature, so the same current flows through both.
How does that change things?
Dramatically. At startup, the motor isn't spinning fast, so it draws a lot of current, since that high current goes through both the armature and the field winding.
The magnetic field gets really strong.
Super strong, which means you get massive starting torque. Really powerful for getting heavy things moving, like trains or cranes.
But what about the speed? Does it stay constant?
No, far from it. As the motor speeds up, the current naturally decreases. And since the field strength depends on that current, the field weakens. A weaker field means the motor has to spin faster to generate the countervoltage, the back EMF.
So speed varies a lot with load.
Hugely. In fact, if you run a series motor with no load at all, the current drops very low, the field gets very weak, and the speed can increase dangerously high. They can literally tear themselves apart. You never run them unloaded.
Wow, okay. Good to know. Starting these things. Especially shunt motors. You can't just connect them directly to the power, can you? Why not?
Because when the motor is stopped, there's no rotation, so there's no back EMF being generated yet.
Back EMF. That's the voltage the motor generates itself as it spins, opposing the supply voltage.
Exactly. Without that back EMF at standstill, the only thing limiting the current is the very low resistance of the armature winding itself.
So you get a huge surge of current.
Massive. Enough to potentially burn out the windings or damage the commutator, so you need a starter.
Like that 3-point starter mentioned in the sources.
Yeah, that's a classic type for shunt motors. It basically inserts a variable resistance in series with the armature at startup.
To limit that initial current.
Right. As the motor speeds up and generates its own back EMF, you gradually cut out that starting resistance section by section until the motor is connected directly to the supply.
And then no-volt release. What's that for?
That's a safety feature. It's usually an electromagnet holding the starter handle in the run position. If the power fails, the magnet releases. The handle springs back to off, and the starting resistance is reinserted.
Ah, so the motor doesn't suddenly restart at full voltage when the power comes back on.
Precisely. Prevents that dangerous high current surge again.
This back EMF seems really central to how motors work. How does it help regulate things?
It's fundamental. The back EMF is directly proportional to the motor's speed. So if you put more mechanical load on the motor shaft, it naturally starts to slow down a bit.
Okay.
As it slows down, the back EMF decreases. Less back EMF means there's a larger net voltage across the armature. Supply voltage back EMF.
Which lets more current flow in.
Exactly. More current flows from the supply into the armature. More current means more torque. So the motor automatically draws more power and generates more torque to match the increased load. It's beautifully self-regulating.
Clever. What about stopping them? Sometimes you need to brake a motor quickly.
Yep, several ways. Rheostatic braking is common. You disconnect the motor from the supply and connect a resistor across the armature terminals.
So the motor becomes a generator.
Essentially, yes.
Right.
Its own inertia keeps it spinning for a bit. As it spins, it generates voltage, driving current through that external resistor. The kinetic energy gets turned into heat in the resistor.
And that slows it down. What's regenerative braking?
That's even smarter, especially for things like electric vehicles or elevators. Instead of just wasting the energy as heat, you arrange things so the electrical energy generated by the motor during braking is fed back into the power supply.
Recovering energy.
Exactly. You get braking and you recover some energy. Win-win.
Okay, that covers DC motors pretty well. Let's shift to AC motors. Induction motors are the big ones there, right? Used everywhere.
Absolutely. They are the workhorses of industry. Robust, relatively simple, reliable.
What's the core principle? How do they work without commutators?
They rely on a really neat trick, creating a rotating magnetic field in the stationary part, the stator.
How do you make a magnetic field rotate?
You use a three-phase AC power supply. You feed the three phases into stator windings that are physically offset from each other, usually by 120 degrees. As the currents in the three phases rise and fall sequentially, they combine to produce a magnetic field whose direction effectively rotates smoothly around the stator.
Okay, a rotating field in the stator. What about the rotor, the spinning part?
The rotating stator field sweeps across the conductors in the rotor. Just like in a generator, this relative motion induces a voltage, and therefore a current, in the rotor conductors.
And those rotor currents create their own magnetic field.
You got it. Now you have two magnetic fields, the rotating stator field and the field created by the induced rotor currents. They interact, creating a torque that makes the rotor spin.
Trying to catch up with the rotating stator field?
Exactly. It's always chasing it, but it never quite catches up.
Why not?
Because if it did reach the same speed as the rotating field, synchronous speed, there would be no relative motion between the stator field and the rotor conductors. No relative motion means no induced voltage, no induced current, no rotor magnetic field, and therefore no torque.
Ah, so it has to spin slightly slower.
Yes, that difference in speed between the rotating field, synchronous speed, and the actual rotor speed is called slip. Slip is essential for an induction motor to produce torque.
Okay. Now, the sources talk about squirrel cage and slip ring rotors. What's the difference?
It's all about the rotor construction. A squirrel cage rotor is the simpler one. It has conductive dars, maybe aluminum or copper, embedded in the rotor core, and they're all shorted together at both ends by conducting rings.
Looks like a cage?
Kinda, yeah. Hence the name. Very robust, no external connections needed. Most common type.
And slip ring.
A slip ring rotor has actual insulated windings, similar to the stator, but wound on the rotor. The ends of these windings are brought out to slip rings mounted on the shaft. Brushes ride on these slip rings, allowing you to connect external circuits, specifically resistors, to the rotor winding.
Why would you want to connect resistors to the rotor? What does that achieve?
It's mainly about starting torque. A standard squirrel cage motor has okay starting torque, but sometimes you need more, especially for loads that are really hard to get moving initially.
Like crushers or big conveyors?
Exactly. By adding external resistance to the rotor circuit via the slip rings at startup, you can significantly increase the motor's starting torque.
How does adding resistance increase torque? Seems counterintuitive.
It changes the phase relationship between the rotor voltage and rotor current, bringing them more into phase at low speeds, which maximizes the torque produced. It also limits the very high starting current you'd otherwise get.
So you add resistance to start, then take it out as it speeds up.
Yep. You gradually reduce the external resistance as the motor accelerates, and eventually you short-circuit the slip rings so it runs like a more efficient induction motor at normal speed. This gives slip ring motors that high starting torque capability that squirrel cage motors lack.
Makes sense. How about controlling the speed of these induction motors once they're running? Seems less straightforward than DC.
It is a bit trickier. The main speed is set by the supply frequency and the number of poles in the stator winding. So one way is to actually switch the connections to change the number of active poles. That gives you discrete speed steps.
Not continuous control then.
Not with pole changing, no. For smooth, continuous control, the most common method nowadays is to vary the frequency of the AC supply using an electronic device called a variable frequency drive, or VFD.
Ah, VFDs. You see those everywhere now.
They're incredibly versatile.
Yeah.
Change the frequency, you change the synchronous speed, and thus the motor speed. For slip ring motors, you can also control speed by varying that external rotor resistance, which changes the slip, but it's generally inefficient because you're just wasting energy as heat in the resistors. VFDs are usually preferred.
Okay, let's move on to synchronous motors. The name suggests something about speed.
Exactly. Synchronous motors run at a perfectly constant speed, called the synchronous speed, which is locked directly to the frequency of the AC power supply and the number of poles. No slip involved, unlike induction motors.
Locked to the frequency, how do they achieve that?
The rotor isn't just relying on induced currents. It has its own magnetic field, created by feeding a separate DC current into windings on the rotor. This DC-excited rotor magnet essentially gets locked magnetically with the rotating magnetic field produced by the stator. They rotate in perfect sync.
So you need that separate DC supply, called excitation.
Yes, you need DC excitation for the rotor field.
And these motors have an interesting property related to power factor.
They do. That's one of their key advantages. By adjusting the amount of that DC excitation current in the rotor.
You can change how the motor interacts with the power grid.
Precisely. You can make the synchronous motor draw current that is lagging the voltage, like an inductor, in phase with the voltage, unity power factor, or even leading the voltage like a capacitor.
Why would you want it to act like a capacitor?
Many industrial loads are inductive, like induction motors, causing a lagging power factor on the grid, which is inefficient. By running a synchronous motor overexcited, so it operates at a leading power factor, it can compensate for the lagging power factor of other loads nearby.
Power factor correction, improving overall system efficiency.
Exactly. Makes them valuable not just for driving loads at constant speed, but also for grid support.
How do they start, though? If they need to be in sync, they can't start from zero like that.
Good point. They have zero starting torque on their own. You need a way to get them up to near synchronous speed before applying the DC excitation to lock them in.
How's that done?
A common method is to include damper windings or amortisseur windings in the rotor pole faces. These look and act like a squirrel cage winding.
So it starts like an induction motor.
Basically, yes. It uses the damper windings to accelerate up towards synchronous speed. Once it's close, you apply the DC excitation and it pulls into synchronism. Another way is to use a small, separate auxiliary motor to spin it up first.
Okay. And the sources mentioned a whole zoo of special purpose motors, too.
Yeah, beyond the main types, you get motors designed for very specific jobs. Servo motors, for example.
What are they for?
High precision control. Think robotics, CNC machines, anything where you need very accurate control over position, speed, or acceleration. They respond rapidly to error signals.
Then there were Schrage motors.
Those are interesting, kind of specialized AC commutator motors. They actually allow you to adjust both speed and power factor, all within the motor itself. Quite complex, though.
Sepper motors. Sounds like they move in steps.
Exactly what they do. They rotate in precise, discrete, angular increments or steps.
Yeah.
Perfect for things like printers moving the print head, scanners, any kind of precise positioning task.
And linear induction motors, not rotating.
Right. Imagine unrolling a regular induction motor and laying it flat. Instead of producing torque and rotation, it produces linear force and motion directly along a track, using some high-speed trains, baggage handling systems, things like that.
Fascinating range. Okay, let's circle back to generators. We know the basic principle, mechanical in, electrical out. Let's look at DC generators first.
Okay. DC generators use the same core idea, rotating armature coils in a magnetic field, inducing voltage. And again, they need that commutator.
But this time the commutator acts as a rectifier.
Exactly. The voltage induced in the rotating armature coils is naturally AC, alternating back and forth. The commutator switches the connections to the external circuit at just the right moments to ensure the output voltage at the brushes is always in the same direction producing DC. It's a mechanical rectifier.
Now, some DC generators are self-excited. How do they start generating voltage from nothing? Where does the initial magnetic field come from?
It relies on a tiny bit of residual magnetism left in the iron poles of the generator from when it last operated. A very weak, leftover field.
Just enough to get things started.
Just enough. When the armature starts spinning, this weak residual field induces a very small voltage in the armature coils.
Okay.
If the field winding is connected correctly, this small voltage drives a small current through the field winding. This small current strengthens the magnetic field slightly.
Which induces a slightly larger voltage.
Exactly, which drives a bit more field current, which makes the field stronger still. It's a positive feedback loop. The voltage builds up progressively until it reaches its normal operating level, limited by magnetic saturation and the field circuit resistance.
Does it always work?
Not always. The field winding has to be connected with the right polarity to aid the residual magnetism, not oppose it. And crucially, the total resistance in the field circuit must be below a certain critical resistance.
Yeah.
Too much resistance, and the small induced voltage won't be able to drive enough current to overcome it and build up the field.
Yeah, the critical resistance. Okay. And just like motors, DC generators come in different types based on the field connection.
Yep. Shunt generator, field in parallel with armature. Series generator, field in series. And compound generators, which have both shunt and series field windings connected in various ways.
Giving different output voltage characteristics under load.
Right. A shunt generator's voltage tends to drop a bit with load. A series generator's voltage can rise initially, and compound generators can be designed to have relatively flat voltage or even rising voltage with load, depending on the balance between the shunt and series fields.
Okay, let's move to the big ones. AC synchronous generators, or alternators, the heart of power plants.
Right. These generate the AC power for the grid, again, based on electromagnetic induction. But here, it's usually the magnetic field that rotates, and the armature windings where the voltage is induced are stationary in the stator.
So the rotor creates the magnetic field.
Typically, yes. The rotor is essentially an electromagnet energized with DC current, excitation, just like synchronous motors. As this magnetic field rotates, it sweeps past the stator windings, inducing that sinusoidal AC voltage.
And the frequency depends on the rotation speed and poles.
Correctly. Grid frequency is tightly controlled, like 50 hertz or 60 hertz, so the speed of the alternator must be kept very constant.
The rotors themselves can look different based on the sources, salient and non-salient poles.
Correct. Salient pole rotors have distinct protruding poles. Think like magnets sticking out. They're generally used for lower to medium speed alternators, maybe driven by hydroturbines or diesel engines. They're physically larger in diameter.
And non-salient.
Non-salient pole rotors are smooth, cylindrical. The field windings are embedded in slots cut into the rotor surface. These are mechanically stronger and better balanced for very high speeds, like those driven by steam turbines in large power plants, sometimes called cylindrical rotors.
How do they get that DC current onto the rotating rotor? Excitation systems.
Yeah, that's crucial. Older systems used a separate smaller DC generator called an exciter, often mounted on the same shaft. Its DC output was fed to the main rotor field via slip rings and brushes.
Prone to wear and tear, I imagine.
They require maintenance, yeah. So modern systems often use static excitation or brushless excitation. Static systems use rectifiers to get DC power from the alternator's own output or an auxiliary source.
And brushless.
Brushless exciters are clever. They have a small AC generator, the exciter, on the same shaft, but its armature is on the rotor and its field is stationary. The AC output from the exciter armature is rectified by diodes, also mounted on the rotating shaft, and this DC current is fed directly into the main alternator field winding on the same rotor. No slip rings or brushes needed for the main field current. Much more reliable.
Okay. Getting the right voltage and a clean waveform out, that involves careful stator winding design, right? Terms like coil span factor, distribution factor.
Exactly. These factors account for how the windings are actually placed in the stator slots. A full-pitch coil would span exactly 180 electrical degrees. Often coils are short-pitched, spanning slightly less.
Oh, I do that.
Short pitching helps to eliminate or reduce certain unwanted harmonics in the output voltage waveform, making it closer to a pure sine wave. That's the coil span factor or pitch factor.
And distribution factor.
That accounts for the fact that the coils belonging to one phase are usually distributed across several slots around the stator periphery, rather than all being concentrated in one big slot.
Also for a better waveform.
Yes. Distributing the winding also helps reduce harmonics and makes better use of the stator surface. The overall winding factor is just the product of the pitch factor and the distribution factor, and it affects the magnitude of the induced voltage.
Now, when the alternator is supplying current to a load, that current flowing in the stator windings creates its own magnetic field, doesn't it?
It does, and that field interacts with the main magnetic field produced by the rotor. This effect is called armature reaction.
Does it help or hinder the main field?
It depends entirely on the power factor of the load the alternator is supplying.
How so?
If the load is purely resistive, unity power factor, the armature reaction field is mostly cross-magnetizing, meaning it distorts the main field but doesn't significantly strengthen or weaken it overall.
What about inductive or capacitive loads?
If the load is inductive, lagging power factor like most motors, the armature reaction has a significant demagnetizing effect, weakening the main field and causing the terminal voltage to drop more. If the load is capacitive, leading power factor, the armature reaction can actually be magnetizing, strengthening the main field, and potentially causing the voltage to rise. Understanding armature reaction is key to predicting voltage regulation.
Voltage regulation. That's how much the voltage changes from no load to full load.
Exactly. It's usually expressed as the percentage change in terminal voltage when full load is applied compared to the no-load voltage, assuming constant field excitation and speed. Lower regulation is generally better, means the voltage stays more stable.
How do engineers figure out the internal characteristics, like the impedance of the alternator? Seems hard to measure directly.
They use indirect methods, primarily two tests, the open circuit test, OCT, and the short circuit test, SCT.
What do these tell you?
In the OCT, you run the alternator at rated speed with no load connected and measure the terminal voltage as you vary the field current. This gives you the open circuit characteristic curve.
And the short circuit test.
In the SCT, you again run at rated speed, but you short circuit the armature terminals through ammeters. You then carefully increase the field current from 0 and measure the short circuit armature current. This gives the short circuit characteristic.
And combining these results.
From the OCT and SCT data, you can calculate the synchronous impedance and synchronous reactance of the alternator. These represent the internal impedance that causes voltage drops under load. It's a crucial parameter for performance analysis and modeling.
Finally, for the grid, you often need multiple alternators working together in parallel. What's needed to connect them safely?
Synchronization. It's critical. Before you close the switch to connect an incoming alternator to the grid, or another alternator, several conditions must be met simultaneously.
What are they?
First, the voltage magnitude of the incoming machine must be equal to the grid voltage. Second, the frequency of the incoming machine must be exactly equal to the grid frequency. Third, the phase sequence must be the same. And fourth, the phase angle of the incoming machine's voltage must be momentarily aligned with the grid voltage at the instant the connection is made.
Get any of those wrong.
And you can get huge circulating currents, potentially damaging the machines and causing major disturbances. Synchronization requires careful measurement and control.
Right. Okay, that's generators covered. Let's tackle the final category. Transformers. We know they change AC voltage using mutual induction.
That's the core principle. You have at least two coils, electrically separate, but linked by a shared magnetic core, usually made of laminated iron or steel.
Primary and secondary windings.
Yep. You apply AC voltage to the primary winding. That drives an alternating current, which creates a continuously changing magnetic flux in the core.
And that changing flux cuts across the secondary winding.
Exactly. Inducing an alternating voltage in the secondary winding. The magic is, the voltage ratio is determined almost entirely by the ratio of the number of turns in the two windings.
More turns on the secondary means higher voltage out.
Higher voltage, lower current capability. Fewer turns on the secondary means lower voltage, higher current capability. Power stays roughly the same, ignoring losses.
Let's talk construction. The core and windings. Why laminated steel?
The core provides an easy path for the magnetic flux to link the windings. It needs to be a magnetic material, like silicon steel. It's laminated, made of thin sheets insulated from each other to drastically reduce eddy currents.
What are eddy currents?
They're unwanted circulating currents induced within the core material itself by the changing magnetic flux. These currents just generate heat, an I²R loss, and waste energy. Laminations break up the paths for these currents. Silicon steel also helps reduce another core loss called hysteresis loss.
In the windings, how are they arranged?
Usually copper wire, insulated. They're wound around the core legs. Common designs are core type, where windings surround the core legs, and shell type, where the core surrounds the windings. Often the low voltage winding is placed closer to the core, and the high voltage winding outside it, which can help with insulation.
You stressed earlier how vital transformers are for the power grid. Can you expand on that? Why are they so indispensable?
It really comes down to efficient transmission. Generating power is often most economical at, say, tens of thousands of volts. But to send that power hundreds of miles, You want much higher voltage, hundreds of thousands, even close to 1,000,000 volts.
Why so high?
Because for the same amount of power transmitted, if you increase the voltage by a factor of 10, the current decreases by a factor of 10. Power loss in the transmission lines is proportional to the current squared, also ITAS. So decreasing the current by 10 reduces the power loss by a factor of 100.
Wow, that's a huge saving.
Massive. Transformers make this possible. Step-up transformers at the power plant boost the voltage for transmission. Then, at substations closer to towns and cities, step-down transformers reduce the voltage in stages.
Down to the levels we use in homes and industry, like 240V or 120V.
Exactly. Without efficient, reliable transformers, our large-scale, interconnected AC power grids simply wouldn't work the way they do. They enable economical generation, efficient transmission, and safe utilization.
Okay, let's revisit that turns ratio, the relationship between turns, voltage, and current.
Right. The voltage ratio is approximately equal to the turns ratio. So VPV is NP&S. Primary voltage over secondary voltage equals primary turns over secondary turns.
And current.
Current is inversely proportional. IPA is NEEP-NP. If you step voltage up by 10 times, you step current down by 10 times, ignoring losses. Power in, VP-NS, roughly equals power out.
Now, even with no load connected to the secondary, you mentioned a small current flows in the primary, the exciting current.
That's right. It's needed for two things. First, it provides the energy to cover the core losses, the hysteresis and eddy current losses happening continuously in the magnetic core as long as it's energized.
Just keeping the core magnetized takes energy.
Yes. And second, part of that exciting current actually creates the magnetic flux in the core. You need that changing flux to be ready to induce voltage in the secondary if a load is connected. It's usually quite small compared to the full load current. And interestingly, because of the nonlinear way iron magnetizes hysteresis, this exciting current isn't usually a perfect sine wave, even if the voltage is.
To analyze transformers, engineers use an equivalent circuit. What's the idea there?
It's a way to model the real transformer with ideal circuit components. It includes resistances to represent the winding wire losses, reactances for the magnetic leakage flux that doesn't link both windings, and components in parallel to represent the core loss and the magnetizing current.
Why model it like that?
It allows you to predict performance. By converting all the secondary side impedances to look as if they were on the primary side, using the turns ratio squared, you get a single circuit you can analyze using standard AC circuit theory. You can calculate voltage regulation, how much the voltage drops under load, efficiency, and things like that, without having to build and test every possible scenario.
So what actually happens inside when you do connect a load to the secondary? Current flows out.
Right. Current throws in the secondary winding to the load. Now, the secondary current creates its own magnetic flux in the core. Lenz's law tells us the secondary flux will oppose the original flux set up by the primary's exciting current.
So the core flux tries to decrease.
It tries to, but it can't really, because the voltage induced in the primary must always nearly balance the applied primary voltage. So to counteract the opposing flux from the secondary current, the primary winding automatically draws more currents from the supply.
An additional primary current.
Exactly. Let's call it anchor. This extra primary current creates a flux that perfectly cancels out the opposing flux from the secondary current. The net result is the core flux stays almost constant, but the primary now draws both the original exciting current plus this load component, AKI, that reflects the secondary load. Ampere turns balance. MP, EPI, NEA. Can PES.
Clever balancing act. Now, transformers are efficient, but not perfect. What are the main energy losses?
Two main categories. First, iron losses, or core losses. These are the hysteresis and eddy current losses happening in the magnetic core. They depend on the voltage and frequency, so they're roughly constant whenever the transformer is energized, regardless of the load.
Okay, constant losses. What's the other type?
Copper losses, or winding losses. These are simply the IOR losses heat generated due to current flowing through the resistance of the copper or sometimes aluminum windings.
So these depend on the current?
Exactly. They are proportional to the square of the current. So copper losses increase significantly as the load on the transformer increases.
When is the transformer operating at its peak efficiency?
Maximum efficiency occurs at the load level, where the copper losses, which increase with load, become equal to the constant iron losses. Transformer designers often aim for this point to be around the typical operating load of the transformer.
And overall efficiency is high.
Very high, especially for large ones, often 98%, 99%, or even higher. Having no moving parts really helps minimize losses compared to motors or generators.
How do engineers measure these losses and find the parameters for that equivalent circuit you mentioned?
Using those two standard tests again, the open circuit OC test and the short circuit SC test.
What does the OC test measure?
You apply rated voltage to one winding, usually the low voltage side for safety convenience, and leave the other winding completely open. You measure the input voltage, current, and power. Since the current is very low, just the exciting current, the copper losses are negligible. The power measured is essentially just the iron losses. From the voltage and current, you can also figure out the magnetizing reactance and core loss resistance components of the equivalent circuit.
And the SC test?
For the short circuit test, you short circuit one winding, again, usually the low voltage side, and apply a reduced voltage to the other winding, just enough to cause the rated full load current to flow in the windings. You measure this voltage, current, and power.
What does that tell you?
Because the applied voltage is very low, maybe 5–10% of rated, the magnetic flux in the core is also very low, so the iron losses are negligible this time. The power measured is almost entirely the full load copper losses. From the voltage and current, you can calculate the total equivalent impedance, resistance, and leakage reactance of the windings.
So those two tests give you all the key loss components and impedance values.
Pretty much everything you need for the equivalent circuit and performance calculations.
Okay. Sources mention different types of transformers too, like power versus distribution.
Yeah. Power transformers are the big ones used in transmission substations, handling very high voltages and power levels. Distribution transformers are the smaller ones you see on utility poles or pads in neighborhoods, stepping voltage down to final usable levels.
And instrument transformers, PTs and CTs.
Right. Potential transformers, PTs, step down high voltages to safe low levels like 120V for metering and relays. Current transformers, CTs, step down high currents to safe low levels like 5A or 1A for the same purpose. They isolate the measurement and protection equipment from the dangerous high-voltage current circuits.
Can you connect single-phase transformers to work with three-phase power?
Absolutely. You can use banks of 3 identical single-phase transformers connected in various ways. Common connections are star-star, Y-Y, delta-delta, star-delta-Y, and delta-star.
Why different connections?
Each has different characteristics regarding voltage-current relationships, handling of harmonic currents, grounding possibilities, and suitability for different applications. For example, delta star is very common for stepping down to supply standard three-phase and single-phase loads.
What's the open delta connection?
That's a way to provide three-phase power, using only 2 single-phase transformers connected in a D-shape. It's sometimes used as an emergency measure if one transformer in a delta bank fails. It works, but the power capacity is reduced to about 58% of the original 3-transformer bank rating.
Can you run transformers in parallel, like alternators, to increase capacity?
Yes, definitely. Both single-phase and three-phase transformers can be paralleled, but again, conditions apply.
Similar conditions to alternator.
Very similar. They must have the same voltage ratio. Their polarities for single-phase or phase sequence and phase displacement for three-phase, determined by the connection type like Y, must be compatible. And ideally, their percentage impedances should be very close.
What happens if impedances don't match?
If the percentage impedances are different, the transformers won't share the total load in proportion to their kVA ratings. The one with the lower impedance will tend to take more than its share of the load, potentially overloading it, while the other runs underloaded. Unequal voltage ratios can also cause circulating currents even under no load.
Okay. Then there are auto transformers. How are they different? They only have one winding.
That's the key difference. An auto transformer uses a single winding, and part of that winding is common to both the primary and secondary circuits. You connect the input voltage across the whole winding, or part of it, and tap off the output voltage from a different point along the same winding.
What's the advantage?
Because part of the winding carries both primary and secondary current, and power is transferred both inductively and conductively, they can be significantly smaller, lighter, and cheaper than an equivalent 2-winding transformer, especially when the voltage ratio is close to 1, like changing voltage by only 10 or 20%.
Where are they used?
Often used for things like motor starting to provide reduced voltage, interconnecting power systems at slightly different voltage levels, or as variable transformers, variacs, where you can adjust the tap position. The downside is there's no electrical isolation between primary and secondary.
Lastly, transformers get hot because of those losses. How are they cooled?
Cooling is crucial. Small ones might just be air-cooled, maybe with fans for forced air cooling, AF. Larger ones are almost always immersed in mineral oil inside a sealed tank.
What does the oil do?
2 main things. It's a much better electrical insulator than air, allowing for more compact winding design. And it's the primary coolant. It transfers heat from the hot windings and core to the tank walls through natural convection.
And how does the tank get rid of the heat?
For medium sizes, the tank might have cooling fins or tubes to increase the surface area for natural air cooling. ON oil, natural, air natural. For larger ones, you might add fans blowing on the radiators. ONF, oil, natural, air forced. Really big ones might have pumps to force the oil circulation through the radiators. OFAF, oil forced, air forced. Or even use oil-to-water heat exchangers. OFWF.
And final components, the conservator and breather. What are they for?
As the transformer heats up and cools down with load changes, the oil inside expands and contracts. The conservator is a small auxiliary tank mounted above the main tank, only partly filled with oil. It provides space for this oil expansion and contraction without exposing the main body of hot oil directly to the air.
Prevents oxidation.
Helps with that, yes. And the breather is connected to the airspace in the conservator. As the oil level changes, air is drawn in or expelled. The breather contains a drying agent, usually silica gel beads.
To remove moisture from the incoming air.
Exactly. Moisture is terrible for transformer oil. It drastically reduces its insulating strength. The breather ensures only dry air enters the conservator, protecting the oil and the transformer's insulation integrity.
Wow, okay. Learner, that was genuinely a deep dive. We've covered, well, a huge amount of ground on electrical machines.
We really have, from the basic forces up to the details of generators, motors, transformers. These devices are just fundamental.
They really are the workhorses, aren't they? Quietly converting energy based on these elegant electromagnetic principles. Hopefully you now have a much clearer picture of how they operate and what makes them different.
Yeah, a solid foundation on the core ideas.
You know, the thing that always gets me is the transformer. It just sits there, seemingly simple, static, yet it's the absolute linchpin of the entire power grid, enabling all that efficient long-distance transmission. It's kind of mind-boggling.
It really is a silent giant, and it makes you think about how these fundamental machines are still evolving, doesn't it?
How so?
Well, think about brushless DC motors. Huge improvements in efficiency and control, especially for EVs and robotics, or advances in motor drives, or how transformer designs are adapting to handle things like renewable energy integration, which can be more variable.
That's a great point. It prompts the question for you, learner. Where do these principles pop up in your areas of interest, maybe in surprising ways?
Yeah, how might these core ideas be leveraged for new innovations? What's the next evolution going to look like based on these same fundamental concepts?
Could be interesting future deep dives, maybe exploring specific motor types like permanent magnet motors or the real nitty-gritty of grid-scale transformers, or even looking at cutting-edge stuff like superconducting machines.
Lots of possibilities.
Definitely. So, learner, let us know what sparks your curiosity for next time. Thanks for joining us on this deep dive.